Okay, this is 6.2, designing experiments. We have talked about the placebo effect before. Remember that this is a placebo is just a fake treatment, and the placebo effect is when a patient claims they feel better after taking a fake treatment, even though it doesn't necessarily work. An example is 42% of men saw an increase in hair growth or didn't lose more hair after taking a placebo when they were told that they might possibly be having a hair regrowth pill. So you can see that this is a very strong effect, and so we always need to control our experiments by having some kind of placebo or fake treatment to make sure that it's just not all in somebody's head. One of the most important things in an experiment is making sure that we control it for outside variables so that we are not seeing effects that we don't want to see. So we want to make sure that we're holding everything constant except for maybe one or two things that we're testing for. And so here are some terms that you need to know. When just the patient doesn't know if he has a placebo or the real drug, that's called single blind. So if you have a doctor who is giving two patients a different type of treatment, maybe it's a diet pill or something. So maybe one person is getting a real diet pill and the other person is getting a sugar pill. And the patients don't know who's getting what, but the doctor does. That's called single blind. Sometimes that's not enough information or not enough control for us. So if the patient doesn't know who's getting what drug and the person issuing the drug doesn't know who's getting one, this is called double blind. Okay? And you may wonder, how does that even work? Well, let's say you're a doctor and you hire an aide to come in and issue the drugs, and each day you just give the aide somebody, this is for person A and this is for person B, and you don't tell the aide who's getting the treatment and who doesn't. And the reason why this matters is if you are a doctor, and maybe not weight loss is that serious, but maybe you're treating somebody for cancer with an experimental drug or leukemia or something like that. If you're giving somebody who's very, very sick a fake drug, it may show on your face. I mean, you may come across as, feeling sorry for them, and then the person can figure out that they have that placebo. So even though it sounds kind of mean, it's better if the person giving the drug can't make that person know at all, so that the drug can just be the only thing that might be making the change. So we all know that when we study surveys, we have issues with gathering data. When we do surveys, and you go to, say, Chick-fil-A and you get that little survey at the bottom, people only respond if they had like a really bad visit and they want to complain, or Chick-fil-A is offering a free sandwich if you do it. And so if the prize is good enough, sometimes we respond to those surveys. In experiments, we get the same kind of issue. So first of all, we could fail to get enough data from all the ethnic groups and genders. So maybe you only experiment on males and you don't know how it would affect females. Or maybe you did whites and blacks, but you didn't do Asians or Hispanics or different things like that. So you want to make sure that you get a good representative of an ethnic group and gender, especially if we're talking about medicine or anything like that. You also can have people refuse to participate. So they may say, oh, look, you have cancer. Would you like to be in our study? And the person could say, oh, wait, I might get a placebo, and then I could just get worse and worse and die. So no, thank you. I don't want to be in your study. So that's called a refusal to participate. We also have non-adherers and dropouts. So non-adherers are people who start off in the study and they start off doing great, but if you have to, say, take a pill in the morning and the night, maybe they forget one day to take it in the morning, and maybe the next day they forget to take it in the night, and they're just not very consistent with the treatment. Or, if you're doing a diet program, maybe they say exercise for 30 minutes, and these people start off great, and then, as time goes on, it gets less and less, and then they don't exercise at all. And then we also have dropouts, and those are people who start the study, they're doing the study, but maybe their time commitment or maybe their health, they start feeling bad, and so they just drop out of the study altogether. In the past, minorities and women were not asked to be in trials. So now they have laws in place that require people who would do experiments to make sure that they do control by asking women and minorities to be in them. Some ethnic groups and, just people in general, not always, are, excited to participate in trials. They don't want to be experiments. Many black cancer patients are hesitant to participate in clinical trials. And so there's little data on, black people with cancer because of this. So there's a lot of things going on that can affect why our experiments might not be perfect. All right, so we've already talked about these two. Non-adherers are subjects who participate but don't follow the experimental treatment, and dropouts are those who begin the experiment but do not complete it. This can cause bias in our experiment, since when we first started the program, we had, so many getting this treatment and so many getting that treatment, and now our numbers might not be even, and that can affect it. So I want you to think for a minute, what is the difference between refusals, non-adherers, and dropouts in an experiment? And why should a researcher be concerned about these groups? So write this down in your binder. See if you can define these three or give me a basic definition of them. And tell me why researchers care so much about these. All right, so remember that somebody who is a refusal just won't start the experiment to begin with. A non-adherer does start the experiment, but they don't do exactly what the researcher is asking, and they stay in the study. Dropouts start the program, but at some point they leave the experiment before it's over. Why would researchers be concerned about these three groups? Well, first of all, if the gender or the race or ethnicity that you need to have in your study refuses to participate, then your study may be illegal, or it may be biased for sure, not having enough of the ethnic diversity in it. If you have non-adherers, this is really kind of annoying for statisticians, because you have them on a set program and they're supposed to be doing it so that you get real data, but they don't even leave the study. So you think they're doing everything right, but of course they're not, and so it may mess up your results. And dropouts, once again, we said this already, but if they start the program and then they leave, then you have that uneven groups, which makes it hard to compare. All right, next. In this study, researchers examined the effect of ultrasound on birth weight. Pregnant women participating in the study group were randomly assigned one or two groups. The first group received an ultrasound, the second group did not. When the subjects' babies were born, their birth weight was recorded, and the women with ultrasounds had heavier babies. So part A asks, is this experiment Double blind or single blind, and why is this important? Well, first of all, we have to kind of remember, well, you may not know, but an ultrasound is the machine that, they put on a pregnant lady's belly, and it shows the baby inside. So a woman could definitely be blinded by this. If they turn the screen away, they could just put like a fake little toy on her belly with a wire on it and like, oh, look, I see your baby. But really nothing's on and nothing's happening. And then, of course, somebody could get a real ultrasound and they would never know the difference. However, it's probably not going to be double blind because the person doing it would obviously see on the screen if it was a baby or if it was fake. To make it double blind, it would be really, really tricky because you would have to replace the equipment without the person knowing, and the person doing it would have to be oblivious to the fact that, when they move the screen might not necessarily be moving in the same direction. So I would say this is probably a single blind. It's important because if the women believed that, an ultrasound would cause heavier children or whatnot, it could start to affect the pregnancy in some way. Maybe she'll start eating more to compensate if she doesn't start gaining weight. Did the experimental design take the placebo effect into account? Yes, it did. The women were blinded to the treatment. And that's exactly what blinding is. They didn't know if they were given the real ultrasound or the fake. And the reason why it's important is it's trying to control that placebo effect. Could you create a better design for this experiment? Maybe. Like I said, if you wanted to make it double blind and you could somehow trick the technician into thinking that they were actually doing a real ultrasound when they weren't, it could possibly make for a better experiment. The whole point of why we do experiments is to see if we can generalize our findings to something that's important. So when they did the whole does cigarettes cause cancer experiments, they wanted to be able to generalize that. They want to say, hey, if you smoke, your chances are going to increase of getting lung cancer or a certain type of cancer. So when can we actually generalize? Well, first of all, it must be statistically significant, and we defined that back in 6.1. And something statistically significant means that what we saw between the control group and the experimental group was so different. So many people got better, or so many people lost so much weight, or whatever it is that we were testing for. Such a big difference that we say, okay, couldn't have been by chance. It must mean that this particular variable does affect what's going on. Secondly, it has to be a well-designed experiment. You have to have control. You have to have that placebo. You have to have a good mix of male and female and the ethnicities, because you don't want to just test for one gender or one race, because different races, different genders carry different tendencies for diseases or things like that. So you want to make sure that it's well designed. And although it's costly, you have to experiment several times. So you don't just do a cancer treatment once and say, well, it must work. No, you've got to keep trying it over and over again. And that's why the FDA or different things like that don't approve things and for a very, very long time. So you have to make sure that your experiment is well documented, it's well controlled, and that it's been repeated several times. Even if you've done all that, you have something that's statistically significant, you've repeated it over and over and over again, and you have a good group of people that you experimented on, your generalization still may be off. So first of all, one reason is a lack of realism when you're doing a controlled experiment. So if you are giving people medication in a hospital, that's very controlled. You can make sure the person is getting the exact amount that they're supposed to get. However, when you issue that drug to somebody in the real world, they very well could forget to take it one day, or take too many, or not enough, or whatever it is. So the conditions of the experiment are very rarely exact to the conditions of the real world. Subjects could be treated too well. So, you know, if you're in the hospital, doctors and nurses are going to come in all the time, check on you, make sure everything's right, and say like your heart rate starts racing when you're taking some kind of drug, they're going to try to fix that. And so once again, it's not very realistic, because you know, once you go home, you don't have that kind of treatment anymore. So let's talk a little bit about the types of experimental designs that you could do. The first is a completely randomized design. The second is called a matched pairs design, and the last one is called a block design. And those are kind of related, but we'll talk a little bit about each. First of all, a completely randomized design is just what it sounds like. You have all your experimental subjects in a big hat, or you give them all of them a number, and then pull a random number generator and start getting numbers, or pull their names out of the hat, and you decide who gets what treatments. So if I wanted to test fabric strength with different laundry, we have different brands that we're going to use, and then we have different water temperatures, because obviously some clothing washing materials work better in hot water, cold water, different things like that. So what we basically do is we have 9 treatments, because treatment 1 is regular Tide with hot water. Treatment 2 is low phosphate Tide with hot water. Ivory and hot water is treatment 3. And as you can see, there are 9 possible combinations of hot, warm, cold, regular Tide, low phosphate Tide, and ivory. Now in each of those, that's not necessarily just one piece of clothing. So maybe they have randomly chosen, you know, some colors, some whites, some delicates, and they put some in each treatment to see how it works. But what they're doing is just completely random. You're pulling numbers and sticking that particular material in that combination of treatments. A food company is preparing to market a new cake mix. It's important that the taste of the cake not be changed by small variations in baking time and temperature. An experiment made from the mixes are baked at 300, 320, and 340 for an hour or an hour and 15 minutes. 10 cakes are going to be baked at each of those combinations, and a panel of taste testers are going to test each cake for texture and taste. So let's go ahead and decide what are our explanatory and what is our response. So the explanatory variables, there's actually 2 here. We have temperature, and if you notice, there was something else. They also are baking it at different times. So one was a little bit longer than the other. The response variable is what are we measuring. So if you notice at the very last sentence, it says the taste testers are scoring each cake for texture and taste. So what we are looking for is texture and taste as our response. Alright, so we want to make a diagram to describe the treatments and how many treatments are needed in all. So this one you could do a chart one, kind of like we did here. You could do maybe the temperatures up here and the times down here, or something like that. Or you could do the ones that we did that had the 2 V's. So either one would be fine. So let's just do a box one, since we haven't done one of those yet. So we have 300 degrees Fahrenheit. We have 320. And we have 340. And we had it for an hour and an hour 15. And we make a table. It kind of looks like this. And we have treatment 1 that has 10, treatment 2 has 10, treatment 3 has 10, 4, 5, and 6. So you see we have 6 treatments like this. If you did it the other way, you would start off like this, and we would have to say random. And notice that I didn't put volunteers here because the cake's not going to volunteer. That just doesn't even make sense. So here, this could be 1 hour, and this could be 1 hour and 15 minutes. And then at 1 hour, we would have to have 3. And once again, these are all randoms. And I'm not going to write it random for all of them because I'm kind of running out of room. But normally you would write random on all 3 lines and random there. And we have 300, 320, 340, and we just repeat here. And then they all come back and we write compare. So either one of these are acceptable, and please know that you don't have to put both of those on an answer. You could just pick one or the other. So that is the table kind, and this is the diagram one. And part B also asks how many cakes are needed in all. Well, up here that makes it really easy. We have 6 with 10, and 6 times 10 is 60 cakes that we would need to experiment on. And part C says, why might it be a bad idea to bake all the 10 cakes for the treatment at once? And why is it better to randomly choose what cake treatment to bake when? So that could deal with the oven variations. So if I only cook all of my 300 for 1 hour in oven A, and I do all of these in oven B, and I do all of these in oven C, well, now I've just introduced another variable, because maybe it's the oven that's affecting it. So, you know, I'd want to do 1 in this oven A, and this in oven A, and this in oven A, and then do maybe number 2 in oven B, and kind of make sure that I do it variation. And also, we don't start off by doing all of these and then all of these, even if it was in the same oven. Because what if the oven got really hot after a while, or maybe something burned out and it got really cold when we started baking the second one. So oven variation is why we want to make sure we bake the cakes randomly. A matched pair design. This compares 2 treatments and chooses a pair of subjects that are closely matched as possible. We assign 2 different treatments to these equally matched groups and we compare. An example could be if I wanted to test if a shampoo is great for a certain type of hair. Now, I could wash a shampoo day 1 with my hair, and then day 2 wash my hair with another shampoo, and then day 3 do my hair with another shampoo. But maybe the effects of day 1 shampoo are starting to come out on day 3, or there's a whole bunch that could go on. So maybe it's better that I find a couple of people who have long hair like me and have the same texture, because I have thick hair. Maybe I'd find more people with thick hair. And, you know, one person would take shampoo A and I would take shampoo B, and somebody else would take shampoo C, and we would use it for a week and we would kind of look at how it works. That's called matched pairs because I've matched people who had similar hair types to mine to do my experiment. Sometimes you can actually be a matched pair with yourself. An example would be if I wanted to see what kind of bug spray worked best. What I could do is spray bug spray A on my left arm and bug spray B on my right arm, and then go out in the middle of summer and see which side gets bitten more. And, you know, I could just keep doing that test over and over and kind of flip-flop, and then, you know, do A on my right arm and B on my left arm the next day, just to make sure, like, the left side of me is not weird or something. But this is called a matched pair with myself. And I guess you could do the shampoo even with a matched pair. If I wanted to wash half my hair with one shampoo and half my hair with the other shampoo. But that's the kind of thing that we're talking about with matched pairs. Something is being compared with it. Either a person with another person who's similar, or you can be compared with yourself. Alright, and block design was the last one we were talking about. A block is a group of experimental subjects that are known before the experiment to be similar in some way that is expected to affect the response. A block design is randomly assigning randomly assignment of subjects to treatments, and it's carried out within a specific block. It is important to know that matched pairs, which we just got done talking about, is an example of block design. It's actually a very specific one because you're being paired only with people who are very similar to you, or hair types that are similar to you, or skin types that are similar to you, or something like that. But block design can be blocked by anything, basically. But anytime you do a block design, you have to decide what you're going to block by and then go ahead from there. So I didn't put in the notes, but blocks can be done by anything. So say like you think, we know that men and women have different hormone levels. So maybe I have this new pill and I think it might affect hormone levels. So I'm going to, first off, before I even experiment anything, I want to make sure I have 60 males and 60 females. And when I have my males, they are going to randomly get equally drug A, B, or C. And then with my 60 females, I'm going to also make sure they randomly get drug A, B, or C. And once I've done that, then I can start to compare. If you notice, I blocked by gender first. I made sure I had an equal number of male and females before I started, and then we went ahead and experimented. We could also do our shampoo experiment by block. Maybe I do people with long hair, and then I do curly hair, and then maybe I do different types of ethnic hair, and I can test like that. But those are blocked. I want to make sure that I have, 100 people with this type of hair and 100 people with this type of hair. Before I even start experimenting on people, I get those in place, and I make sure that each group has the same number of trials in it so that we get a good design and information on that. All right, here's an example. Men and women have different reactions to TV ads. Some women will watch those public commercials and just start crying, and maybe some guys too, I don't know. But a company has created 3 ads, and it's interested in seeing how the ads are going to be received by males and females. And so we're going to set up an experimental design. Now, I had done this, and apparently when it went from PowerPoint to Google Slides, it went crazy. So I'm going to redraw that. Here you could put subjects or volunteers would be effective. But as you notice, the very first thing they did is they put women and men. So they're blocking by gender. We don't stick random here once again. You're a woman, you're a man. It's not randomly decided here. Each one now are going to be randomly assigned to the 3 ads. So now we do write the word random. And once again, write random on all 3 lines. And we have ad 1, 2, and 3 for the women. And we have ad 1, 2, and 3 for the men. And we are going to compare once we're done with the experiment. And we're going to compare once we're done with the experiment. And you could also compare one more time between the men and women if you wanted, but I kind of ran out of room. So you could draw arrows here and write compare one more time to show that we compared the women between the 3, the men between the 3, and then we kind of see, is there any relationship between the 2 of those? So that's what that design should have looked like. Sorry that it's a little bit weird. All right, here's another try this. Nurse practitioners are nurses with advanced qualifications who often act like primary care physicians. Are they as effective as doctors in treating patients with chronic conditions? An experiment was conducted with 1,316 patients who had been diagnosed with asthma, diabetes, or high blood pressure. With each condition, patients were randomly assigned to either see a nurse or a doctor. And 6 months later, we're going to see who is more healthy and have patients take a survey of satisfaction with their care. So first of all, A, is the diagnosis asthma or diabetes or high blood pressure, is that a type of treatment variable or is that a block? Hopefully you know that that is a block. And it should be obvious. But if we're not sure about the terms still, if we haven't studied our terms, then it may be confusing, and you may say, why? Well, a treatment variable is something you give to somebody. So I am not going to go around and give somebody asthma or give somebody diabetes or give somebody high blood pressure. So it's definitely not a treatment variable. It is a block because it is a pre-existing condition. That's a very good way to think about blocks, is they're usually pre-existing conditions. So when I talk about shampoo, my hair is long and thick. That's a pre-existing condition. Now, of course, I could cut my hair short for an experiment if I wanted, but I couldn't make somebody with very short hair have long hair all of a sudden, at least naturally, for my experiment. So blocks are usually pre-existing condition of some kind. You're either female or male, or you're old or you're young. And once again, could you wait for a young person to get old? Yes, but it's just easier to get groups of people who are already in that age. B asks, is type of care a nurse or a doctor, a treatment variable, or a block? Well, a treatment variable is how we are controlling the experiment. Since I cannot give you asthma or diabetes or high blood pressure, I can't control that. So it would just be an observational study if that's all I was looking at. But because I am giving you either a nurse practitioner or a doctor for the next 6 months, that is where it becomes an experiment. And so now that is called a treatment variable. So the type of care is a treatment variable. And why is it a treatment variable? Because it is what was assigned to the patients. So remember, a block is a pre-existing condition. We can't really change it easily. But a treatment variable, we can. I can have you go see a doctor. I can have you see this nurse practitioner. And if I say, oh, it's free if you go see this person for 6 months, most people are going to say, sweet, and take you up on that offer. So that is why a treatment variable is something that's easily moved around, but a block is kind of a pre-existing condition, and we want to make sure we set it up right. Okay, so now we're going to set up our diagram for the experiment. You, once again, really could use a table, or you could use the diagram. It's really up to you which one you like to do. If you decided to do the table, you would do, actually, let's just do a diagram, because that way we were talking about blocking, so that'll make it a little bit easier. All right, so we have volunteers. And we are going to block by the 3 conditions. So our 3 conditions, once again, were asthma, diabetes, and then high blood pressure. I cannot put random here because it's a block. I did not randomly make somebody get asthma or diabetes or high blood pressure. They already had it. It's a pre-existing condition. I just got volunteers who happen to have that. So this does not get the word random on there. Make sure you know that. Each one were assigned then with a nurse practitioner or a doctor. So each one gets assigned to one or the other. Question, would I put random on these lines? Hopefully you said yes, because I can randomly decide who gets what. And remember, each line gets the word random. My pen's being weird, so pretend all those words say random. Once again, once I've done all of that, we are going to come back together and we are going to compare. So there's our diagram, and when we do a diagram, the first things that come first have to be the block if it is a block design. After that, you can go on to the treatment variables. Please don't ever put the treatment variable first and then tell me what the block is, because if you remember in the definition, the block has to be decided first. So if I start randomly assigning people and then I block, I did not follow the directions. I have to block first, then randomly assign them into groups. So make sure you get that straight. Alright, so now you are ready to do your assignment for 6.2. The next thing that will be done will be, after this day, will be an experiment and a quiz over 6.1 and 6.2.